Start of Slide 1. Slide Caption. Chapter 18. Motor Load, Torque and Power Quality Requirements. Section 18-1. Understanding Motor Loads and Torque Requirements. Section 18-2. Power Quality. Section 18-3. Motor Loads. Section 18-4. Motor Torque Types. Section 18-5. Open and closed circuit transition. End of Slide 1. Start of Slide 2. Slide Caption. Objective. Section 18-1. Understanding Motor Loads and Torque Requirements. By the end of this presentation, you should be able to explain why the type of load and torque requirements for a motor must be understood. End of Slide 2. Start of Slide 3. Slide Caption. Motor load types and torque requirements must be understood for both mechanical, magnetic motor starter, and solid-state, motor drive, applications. See Figure 18-1. Since all motors produce torque that can be used to operate loads, all motors are capable of producing work. The amount of work a motor produces depends upon its size, which can range from fractional horsepower to hundreds of horsepower, and the type of load it must drive. In the past, a motor was connected to a motor starter, manual or magnetic, and if the motor produced enough torque to start and operate the load, the exact type of load and required motor torque did not always need to be fully understood. However, in today's motor control systems that use programmable motor drives, the type of load and operating torque requirements of the application must be understood. This is because the type of load and any changes in required operating torque, such as torque boost, are programmed into the drive before the system is operated and when any load requirement changes are made. End of Slide 3. Start of Slide 4. Slide Caption. 18-1. Checkpoint. When a motor drive is used to control a motor, can the drive be programmed to add an additional torque boost if the application requires it? When does a motor draw the highest amount of current from the power supply? End of Slide 4. Start of Slide 5. Slide Caption. Objectives. Section 18-2. Power Quality. By the end of this presentation, you should be able to define voltage fluctuation and describe different voltage fluctuation problems. Explain how to test for transient voltages. End of Slide 5.
Start of Slide 6. Slide Caption. Voltage changes, such as voltage sags and swells, undervoltage, and overvoltage, are difficult to detect because voltage changes are often intermittent. See Figure 18-2. A momentary power interruption is a decrease to 0V on one or more power lines lasting from 0.5 cycles up to 3 seconds. A temporary power interruption is a decrease to 0V on one or more power lines lasting for more than 3 seconds up to 1 minute. A sustained power interruption is a decrease in voltage to 0V on all power lines for a period of more than 1 minute. Voltage changes other than power interruptions occur much more often and can be a continued change that causes both short-term and long-term problems. End of Slide 6. Start of Slide 7. Slide Caption. A voltmeter with a minimum/maximum recording mode is used to determine the type of voltage problem. See Figure 18-3. A voltmeter can be used to measure the voltage at the power source and at the load to determine if there is a problem with bad connections, too long of run, or undersized conductors. Many voltmeters have a min/max recording mode that is used to measure voltage over time and can be used to determine if there is a voltage sag or other voltage fluctuation problem. End of Slide 7. Start of Slide 8. Slide Caption. Transient voltage measurements must be taken anytime equipment prematurely fails and transient voltages are suspected. See Figure 18-4. Transient voltage measurements are taken to verify that surge protection devices are working. A transient voltage measurement is different from a standard voltage measurement because a standard voltage measurement displays the root mean square known as RMS voltage value of a circuit, and a transient voltage measurement displays the peak voltage value of a circuit. For example, a standard voltmeter that displays 115 volts AC is displaying the RMS voltage measurement of the circuit. The peak voltage of a 115 volts AC, RMS circuit is about 162 volts, RMS voltage multiplied by 1.414 equals peak voltage. End of slide 8. Start of slide 9. Slide caption, 18-2. Checkpoint. What is the acceptable operating voltage range, percentage, for newer electrical and electronic equipment? Are voltage sags or voltage swells a more common problem? What is a brownout? What are the two types of transience voltages produced on a power distribution system? End of slide 9. Start of slide 10. Slide caption, objective. Section 18-3. Motor loads. By the end of this presentation, you should be able to describe the different classifications of motor loads. End of slide 10.
Start of slide 11. Slide caption. Loads are generally classified as constant torque / variable horsepower known as CT / VH, constant horsepower / variable torque known as CH / VT, or variable torque / variable horsepower known as VT / VH. See Figure 18-5. Motor loads may require constant torque, variable torque, constant horsepower, or variable horsepower when operating at different speeds. Each type of motor has its own ability to control different loads at different speeds. The best type of motor to use for a given application depends on the type of load the motor must drive. End of slide 11. Start of slide 12. Slide caption. CT / VH loads are loads in which the torque requirement remains constant. See Figure 18-6. A constant torque / variable horsepower, CT / VH, load is a load in which the torque requirement remains constant. Any change in operating speed requires a change in horsepower. CT / VH loads include loads that produce friction. Examples of these loads include conveyors, gear pumps and machines, metal cutting tools, load lifting equipment, and other loads that operate at different speeds. End of slide 12. Start of slide 13. Slide caption. CH / VT loads are loads that require high torque at low speeds and low torque at high speeds. See Figure 18-7. A constant horsepower / variable torque load is a load that requires high torque at low speeds and low torque at high speeds. Since the torque requirement decreases as speed increases, the horsepower remains constant. Speed and torque are inversely proportional in CH / VT loads. End of slide 13. Start of slide 14. Slide caption. VT / VH loads are loads that require different torque and horsepower at different speeds. See Figure 18-8. A variable torque / variable horsepower load is a load that requires a varying torque and horsepower at different speeds. With this type of load, a motor must work harder to deliver more output at a faster speed. Both torque and horsepower are increased with increased speed. Examples of VT / VH loads include fans, blowers, centrifugal pumps, mixers and agitators, and other loads that operate at different speeds. End of slide 14. Start of slide 15. Slide caption. 18-3. Checkpoint. If a drive is used to operate the spool of a paper roller, what setting, CT, VT, or CH, should be used? If a drive is used to operate a variable speed industrial food mixing machine, what setting, CT, VT, or CH, should be used? End of slide 15.
Start of slide 16. Slide caption, objective. Section 18-4. Motor torque types. By the end of this presentation, you should be able to define and describe the types of motor torque. End of slide 16. Start of slide 17. Slide caption. A motor connected to a load produces 4 types of torque: locked rotor torque known as LRT, pull-up torque known as PUT, breakdown torque known as BDT, and full load torque known as FLT. See Figure 18-9. A motor must produce enough torque to start the load and keep it moving for the motor to operate the load connected to it. It bears repeating that the four types of torque are 1. Locked rotor torque, LRT, 2. Pull-up torque, PUT, 3. Breakdown torque, BDT, and 4. Full load torque, FLT. End of slide 17. Start of slide 18. Slide caption: Locked rotor torque is the torque a motor produces when its rotor is stationary and full power is applied to the motor. See figure 18-10. All motors can safely produce a higher torque output than the rated full load torque for short periods of time. Since many loads require a higher torque to start them moving than to keep them moving, a motor must produce a higher torque when starting the load. Locked rotor torque is also referred to as breakaway or starting torque. Starting torque is the torque required to start a motor and is normally expressed as a percentage of full load torque. End of slide 18. Start of slide 19. Slide caption: Pull-up torque is the torque required to bring a load up to its rated speed. See figure 18-11. If a motor is properly sized to the load, pull-up torque is brief. If a motor does not have sufficient pull-up torque, the locked rotor torque may start the load turning, but the pull-up torque cannot bring it up to rated speed. Once the motor is up to rated speed, full load torque keeps the load turning. Pull-up torque is also referred to as accelerating torque. End of slide 19. Start of slide 20. Slide caption: Breakdown torque is the maximum torque a motor can provide without an abrupt reduction in motor speed. See figure 18-12. As the load on a motor shaft increases, the motor produces more torque. As the load continues to increase, the point at which the motor stalls is reached. This point is the breakdown torque. End of slide 20.
Start of slide 21. Slide caption: Full load torque is the torque required to produce the rated power at full speed of the motor. See figure 18-13. The amount of torque a motor produces at rated power and full speed, full load torque, can be found by using a horsepower to torque conversion chart. To calculate motor full load torque, the following formula is applied. End of slide 21. Start of slide 22. Slide caption: A motor may be fully loaded, underloaded, or overloaded. See figure 18-14. If a motor is fully loaded, it produces full load torque. If a motor is underloaded, it produces less than full load torque. If a motor is overloaded, it must produce more than full load torque to keep the load operating at the motor's rated speed. End of slide 22. Start of slide 23. Slide caption: 18-4. Checkpoint. What type of torque is required to produce the rated power for a motor at full speed? What type of torque is required to start turning a motor shaft? End of slide 23. Start of slide 24. Slide caption: Objective. Section 18-5. Open and closed circuit transition. By the end of this presentation, you should be able to explain the difference between open circuit transition and closed circuit transition. End of slide 24. Start of slide 25. Slide caption: Open circuit transition produces a higher current surge than closed circuit transition at the transition point because the motor is momentarily disconnected from the voltage source. See figure 18-15. Closed circuit transition is preferable to open circuit transition because closed circuit transition does not cause a high current transition surge. However, closed circuit transition is the more expensive circuit transition method to attain. End of slide 25.
Start of slide 26. Slide caption: Circuit transition should occur at or near full motor speed to minimize current surges. See figure 18-16. The high current surge during open circuit transition is based on the motor speed at the time of transition. Transfer from the low starting voltage to the high line voltage should occur as close to full motor speed as possible. If the transition occurs when the motor is at a low speed, a surge current even higher than the starting current can occur. End of slide 26. Start of slide 27. Slide caption: 18-5. Checkpoint. What circuit transition method is the least expensive type that can be used? Why is a closed circuit transition preferred when switching a motor from reduced voltage to full voltage? End of slide 27.
Copyrights originated by the publisher with modifications by Nita Leighton and Glenn Graham.